saw yesterday. So each one of these square boxes is where I've used a biomass pool to represent a part of the food web. And these kind of funny shapes are to represent the fact that there's an age structure behind an animal. So you've got little ones on one end and big ones on the other end. So little ones on this end and big ones on the other. Okay? The reason we do that kind of stuff is we don't say where the animals are going to live. We make the rules about how they live, and then our check that the model's working is to see whether the community structure, what animals live where, that comes out of the model matches what we see in reality. So these are the different kinds of community structures you see for a big model we have in Southeast Australia. If you just zoom in on one of those, so there's about 65 groups in this model, but they don't all live everywhere. So we just zoom in the one off Eastern Bass Strait. So this is what the world probably looked like in Atlantis terms back in about 1910, before they started doing a lot of commercial fishing in that part of the world. And then by about the year 2000, it changed that much. So you can see that the small pelagic fish, the little fish, had come up a lot in size. So if we think back to my comment before about the unfished state, they think about it independent of all the other fish in the world. You get completely the wrong idea if you had this version of the world for unfished, without realising that it actually changed from that in the first place. You can also see that some of these groups have changed their structure. So we can pick this one here. It's gone down to that little triangle. So what that's saying is not only have we literally lost some of the large sharks, we've lost the oldest and biggest of those large sharks. So you get a change in the shape of the age structure, and that can be an important detail to try and pick up as well. Okay, so some of the ways that we're starting to use it now is to look at human interactions with the system. So there's a lot of mathematics that makes my ears bleed behind this picture, but basically, if it's above this line, the different pressures work against each other and effectively cancel each other out. If they come out below this line, they're all working in the same direction. So they're either making the animal go up in biomass, like it's increasing, they're all working together to make it increase, or they're all working together to make it decrease. Okay, so if we think of just about temperature and acidification, so if it could play the world forward with no humans in it, but still get the level of temperature change and acidification we're expecting under climate change, around Australia it actually largely cancel each other out. You wouldn't see a huge change in the ecosystem. But you add fishing into it, and it's not just that fishing makes it worse. Fishing changes the interaction effect of acidification and temperature change. They now all act in the same direction to make the situation worse. And what's happened is effectively past fishing that we can't do anything about now. It's happened 50 years ago. If you think of an ecosystem like a melon, it went in and it gutted the melon. So the ecosystem still kind of looks like it's okay. You can see the melon has the right melon shape, it's got the rind, but there's no substance inside it. So once you hit it, it shatters. Its resilience has gone. And that's the synergistic effect of fishing. It means we have to change our fishing rules, which ironically isn't a bad thing. So if we think about Australia's action on climate change versus Australia's action on fishing, it's much easier to change the fishing rules. So we'll start to get those in place a lot faster than we learn from climate change. One of the other bigger things we can look at with something like this is the effect of fisheries-induced evolution. So we've heard about evolution and how a predator can make you want to be faster or bigger or whatever. Well, when fishing comes along, it takes the big one, so it's forcing that species to try and be smaller. So the faster that you can reproduce, you're typically smaller, the more of your genes will get through. So with this kind of fishing pressure that we've got across the bottom here for one of the most common fish species in Southeast Australia, we're actually expecting this level of evolution. So what it means is the average size of the animal is likely to have decreased by up to about 10 centimetres. Now that doesn't sound too bad, except you can think about it that even a couple of centimetre change could reduce the fecundity by as much as 50%. And if they went the whole 10 centimetres, it might drop their ability to have babies by 90%. So if you start, and when you think about the gate limitation, if they're smaller, more things can also eat them. So it has an effect on their mortality. So we played that out as well. And these are five of the most common fish species in Southeast Australia. This is the change in just their predation mortality, not their fishing mortality, as a result. You can see grenadier actually goes down because it sneaks in under the window of a predator. Being smaller actually in that particular case saved it as a juvenile. It could hide better. Most of the others got nailed. And it's equivalent evolution alone was the same as fishing them twice as hard. It wasn't something that we were taking account of in the fisheries. You can see it can have quite large, from the same starting point, it can have quite large effects on the amount of animals that are there. Now, I spent a lot of time talking about what those kind of classical ODE kind of models can do. They don't necessarily do crazy-ass behaviour like this very well. Yep.
For the previous one, you have jellies in there?
Jellyfish? Yes, we have jellyfish.
See the substitute the fish, like think like that.
Jellyfish are a bit like a canary in a coal mine. Pretty much every ecosystem model in the world says if you see jellyfish go up, something's wrong. And we are seeing jellyfish go up, so something's probably wrong. So what we can't do is we can't do this kind of behaviour very well. So this is where I say, that's enough for me, and I leave it to take over. We might as well do some questions to me now while I get set up. Do you have any questions? No, usual stuff. Does that mean I talk too fast? Yeah.
So you talked about migration before, and so it's like that. The problem is that if you want to model migration, you don't really know the mechanism that drives it. But you're just sort of saying, okay, we know the fish should show up here, and so how do you? You don't really know what is it mechanism driving the migration. You just know. So how do you, if you want to have a look at some climate scenarios, how do you actually build it?
Okay, so there's some that we do know what the cause is. It's like spawning and something like that. Some of it they're moving to a good feeding location. So you can start to do that. There's other ones you can do a trick where you correlate. It's all based on correlation, so that's obviously not causation, but we use it as a starting spot. You look at the temperature there, you look at the water properties of the spots they're going to, or the environment, you know, what kind of habitat it's on the environment, what kind of animals are there, how much prey, how hot is it, that kind of stuff. And then you run the climate models forward, and you look to see where those spots will have moved. So you can do that inside an ecosystem model where you've got all the things moving around. Well, lots of people, particularly on land, have just done that full stop at a species level and said, okay, these animals are likely to shift. Someone that works with Rashid has done that for 1,500 animals, so 1,500 kinds of fish species around the world, and looked at what that means for fisheries and biodiversity potentially to the future. So you can use some mathematical tricks without having to know exactly what's driving it. But you do have to be quite conscious that can mean that if what you think is causing that correlation changes, then it might be useful. So until we learn more about it, kind of where we start now.
Over your career, you built models that have started off very simply and then become more and more and more complex to the point where you now have to have a team building these models. Where's the future?
So basically, what you see in something like Atlantis, well, actually, what you see in a lot of these FDM models, if you think of it as a cupboard full of spice in a kitchen, you've got all these different kind of spices, which give you different options on how animals live. You never use all of the spices, otherwise the stew tastes disgusting. So what you want to do is be quite selective about what you pick out, and it has to be dependent on what you're trying to represent. So there will be a lot more elaboration of particular details as we learn more about the climate effects and they become key to representing what we want. But I would never recommend that you turn on all the features in Atlantis or all the features in Ecosystem or anyone else. You have to be quite selective. So a lot of the big models in the climate space have become teams as you get experts in different areas. You're starting to see that in ecology. I've had people come up and say the years of a one-person modelling team are gone. I tend to disagree. If you feel comfortable in being a one-person modelling team and you've got the support pull which you need together, that's fine. But there is certainly an idea in science that you now have to always be in a team. But you have to be really careful. That means you don't just get a super complicated model rather than a complex model that's producing the dynamics that you're after. I use qualitative and conceptual models equally as much as they use a big model. It's kind of a step approach.
Yeah, so I'm sort of half interested in understanding at some stage you're going to reach a time where expert opinion, people who spend all their time in the system, fishermen, pilots, whatever, start into your model as an active component throughout the whole.
Yeah.
Is that where you sit?
Yeah, so when I do a modelling exercise, I sit down with pencil and paper and books at the start, and then I'll take that diagram in my back pocket with me, and then I'll go sit with the fisherman or whoever, and literally in the sand or whatever happens to be the hand, will draw out how they think the world works, and then I'll piece that together with my idea, or if it clashes with what science thinks, we'll discuss that through. And sometimes it's as far as you have to go. So sometimes it might just be a matrix algebra, sometimes you get into like a what's called a minimum realistic, we might have a fish and a temperature or something, or you might need to go the whole way through. There's kind of no recipe book that you always must do this, always, you know, only go as complicated as you need to address the question. But you always need to talk of it to the fishermen and the guys who live in the system. So we have a process in my modelling team called the laugh test. You make a model and then take it to an expert to see if they laugh or not. How far off am I? And sometimes the laughter is because you've completely cocked it up. But sometimes it's because they haven't thought about it. So one of the ones that I always go, yes, I got that one right, was jellyfish was a big part of the tuna diet in one of the Atlantis models for the southeast of Australia. And I went and showed it to the tuna guys and said, does this look sensible? And it's like, oh, you're right, we've never seen that in jellyfish. And I said, well, it's only happening in winter. Can I see the winter data? We've never collected it in winter. So they went out and collected it in winter and they fought jellyfish. So sometimes the models can be what looks like wrong when they're actually right. So you have to double check to make sure the data of the model are talking apples and apples, not apples and oranges. But it's always good to get the experts to be in there. So stop monopolising.